Well, Swampland is for me exciting because it's the executive summary of all I have learned from string theory. If somebody told you, okay, you have studied string theory, tell me what did you learn, what it is that this quantum gravity is all about, this is what Swampland is trying to do. It's exactly the lessons we are supposed to have learned from studying string theory. Now, what does that exactly entail? Quantum gravity is very different from the rest of quantum field theories. So if you take particles like quantum quarks and electrons and how they interact in the context of gauge theories, we have beautiful theories which describe them very nicely. Quantum chromodynamics describes the theory of strong interactions. Quantum electrodynamics does the same for electricity. And there's the electroweak force, which is another kind of gauge force, which is also does as equally a good job for describing the weak forces. Naively, one might have thought the gravity is of the same type. You can take the gravity and do the same thing you do with these other forces, and that just doesn't work. And part of the reason it doesn't work is that a lot of the notions of quantum field theory breaks down when it comes to gravity. Quantum field theory has a hierarchical structure in terms of short and large distance physics. And the idea is that you're always interested in large distance. What happens at large distance, not at microscopic scale. So you kind of integrate out what we say, or basically average out what's happening at short distances to come up with an effective description at larger distances. Sometimes we call this the effective field theory perspective about how things are emerging. This idea works beautifully in quantum field theories. Namely, you start with a given large distance physics and ask what kind of symmetries are operative at that scale. And using symmetry arguments, you can more or less write down what the physical action looks like. Except that you don't need to know what was the short distance physics leading to this theory. So you just ignore it because it's not relevant for your question. So we learned the fact that if you're interested in describing large distance, by and large, you can forget what's going on at short distance. And that is why quantum field theory has become so powerful, because you can just take symmetries and write whatever you want, and at a larger scale, deal with it. Not at even if you don't know the details at short distance, that does not affect your calculation at large distances. Very powerful idea. This idea totally fails for quantum gravity. The idea of separation of scales of short and large, microscopic and macroscopic, is what doesn't work for quantum gravity. And the idea why it doesn't work is one could kind of see why. So let's do the Gedanken experiment. Like, you want to describe what happens at short distances. What we do in particle physics is to take two particles and accelerate them toward each other with ever higher energies. Why? Because when they go at higher energies, they can probe shorter and shorter distances. The distance scale you probe is inversely proportional to the energy in the center of mass of such a collision. So therefore, you go at a higher and higher energy, you collide them to see what's going on at shorter distances, namely what comes out of such a process of scattering these particles. What is created gives you a hint about what's happening at higher and higher energy scales or shorter and shorter distance scales. This is the idea of quantum field theory. If you try to do this for quantum gravity, this begins to work the same way that we think about quantum field theory. You take energies of the particles to go higher and higher until you go to such high energies that something totally unexpected happens. What happens is that instead of particles coming out, suddenly nothing comes out. So you hit them at a very high energy, and what happens instead is that you create a big black hole.
Yes.
A black hole is a solution to Einstein's equation, which is described by long distance physics, not short distance physics. So you are interested in understanding what's going on in short distance, and the physics told you, sorry, you cannot go any further than this. After this scale, everything is becoming bigger. So higher and higher energies is now translating to higher and higher distances, which is opposite to the way of thinking that we had. In other words, high energy and low energy kind of are connected. This discussion of separating the short and large distances in this way fails. So the idea of the effective field theory fails in quantum gravity precisely because of black holes. So the black holes run the show in this case. So this is why quantum gravity is very special. Now I come to Swampland. So this was just a background about the connection between quantum gravity and why is it so different from quantum field theory. So you say, okay, so okay, they are related. So but what does this relation really mean? How do you actually use this fact? What is the description? This means that you cannot just say, I have this and this symmetry in long distances, write down for me the action. That you cannot expect to work. String theory tells you that in fact does not work. In other words, if you just studied with the symmetries, you would have thought about the many, many, many more possibilities than you can actually get from quantum gravity. The short distance physics tells you not all of the things that you thought are okay are actually okay. There's a conspiracy between that short distance and large distance, which is not apparent to a field theorist point of view. How do we know this? String theory. So the examples that we have learned from string theory tells us that the things that we get, no matter how we change. So in the string theory, we choose these extra dimensional geometries because string theory is more than 4-dimensional space-time. These extra dimensions have their own geometries that we can pick. Calabi-Yau, this manifold, that manifold, G2 manifold, spin 7 manifold, whatever. You choose it and you see what physics comes out. You change the manifold, changes the physics. So you say, okay, I want to see a different physics. I want to get this kind of physics. Can you give it to me? The answer is almost always no. The kind of physics you get are very, very restrictive. In fact, among the set of all possible conceivable physical theories that you may have been interested in getting, the ones that you actually get are measure zero. The ratio of what you can get to what you want to get, or you could have wanted to get, is zero. That means it's basically minuscule possibilities of what are actually consistent theories with gravity. So our perspective of what is this fails. Now,
wait, is that a theorem?
Well, we have a lot of evidence. No, there's a lot of evidence for what I just told you. And so in different examples, it's a theorem. Depends on how precise a question you want to ask. So I'll give you a few examples of this. To try to understand what are these restrictions is what we call the Swampland program. Swampland program tells you out of these possibilities, which ones are not good. Swampland. Now, the other ones are good. The ones which are not bad, we call them landscape. So you might say, why are we looking for swampland instead of landscape, which is what the good ones are? The point is that the landscape are measure zero. So it's like saying you have points on a plane and you want to find these points. Well, good luck. What you can more easily say is, well, you draw a line and say to the left, there are points, to the right, there are none. Much easier to do that than to say there is a point exactly there. So Swampland program is trying to find these lines, kind of ideas like to the left is okay, to the right is bad, and this and that. So this narrows what is possible. It doesn't pick you those points because those are very difficult because they're very rare. So that's the Swampland program, is to understand these lines. And I will try to tell you some of these lines or these Swampland criteria that we have found over the years. So the first one, which actually happened even before the Swampland program started even back in the, 40s or 50s, 1940s or 50s by Wheeler and collaborators, which is the statement that no quantum theory of gravity has symmetries other than gauge symmetries. In other words, you cannot have symmetries in quantum gravity without having electrical field associated with them. Like in our universe, we have, of course, electric charge, which is conserved, but that has electrical field with it. So what this statement is that you could not have a universe where there's electric charges with no electrical field coming out of it, and the charges are still conserved. That is a no-no. That's not possible. Now, from the viewpoint of an effective field theorist like you and I, it sounds perfectly fine. Why not? Why can't you have objects you can count but has no electrical field on it? Says quantum gravity says, no, you cannot. So this is almost at the status of a theorem. Why do we think so? Well, because we have ideas having to do with black holes, which tells you that if this was not the case, you would get into trouble because you can send one of these charges to the black hole and black hole evaporates and you get rid of that charge. So therefore you violate the conservation of charge. So symmetries disappear through the black hole evaporation process. And so there are arguments like that. So when you say, can you prove it? Of course, it presupposes we have a framework or principles to prove, but we don't have those. So I cannot tell you I can prove it because I don't have the Euclidean principles like the axioms of Euclid or whatnot. So I cannot give you such a proof. But to the extent that we believe the evaporation of black holes works the way we do, which we are very sure of, this is a proof that there is no global symmetries. Another example is weak gravity conjectures that we have, which we have a huge amount of evidence, which says in any conceivable quantum theory of gravity, gravity is always the weakest force. It's not just in our universe. You could not have had any consistent theory of physics for which gravity was not weaker than other forces. that sounds, again, strange from a viewpoint of effective field theories, because you can imagine having 2 electrons.
So the hierarchy problem is then the hierarchy inevitability?
No, the hierarchy is more specific question. Hierarchy just says, why is the scale so much smaller? It could have been just a factor of 10 smaller.
Oh, I see. Okay.
Hierarchy says, why is a factor of 10 to the 19 or 10 to the whatever smaller? That's a different one. Here we're just saying the scale is lower, but we didn't say how much lower. But it goes in the direction of making hierarchy possible, let's say. It goes in that direction, but it doesn't tell you have to have a huge hierarchy. So this idea, the weak gravity conjecture, if you think about it, it's a little strange why it's true. Because if you imagine you have 2 electrons, well, if you put them at a distance r relative to each other, there's a repulsion between them, which Coulomb taught us. It goes like a square of their charge divided by distance squared. Mm-hmm. Like we call E squared over R squared, the distance squared. But there's also a gravitational attraction between them, which goes like their mass times mass over R squared. That's Newton's gravitational attraction. So it goes like M squared R squared. So gravitational attraction is M squared R squared. Electrical repulsion is E squared R squared. And we are saying repulsion always wins. In other words, M is always smaller than E. Well, you could have imagined that electron's mass was much higher and it would have been the other way. But we say, no, the theory of gravity would not have worked. You see, that's a positive surprise, because you would have thought there's no reason a priori the mass of the electron has anything to do with its charge. This says, no, it better be smaller than its charge in the appropriate units and in the fundamental units in physics. So these kind of ideas, and these are just 2 examples. There are many more examples.
Yes.
Perhaps I would say one more example, because it's also one of the most remarkable examples, which relates to duality symmetries of string theory. This statement, which I find probably the most difficult to see from an effective field theory predictions or perspective, is what is called the distance conjecture or duality conjecture. The statement is that if you take parameters in your theory, first of all the parameters in your theory are dynamical. Now, what does that mean? That means when we usually think about constants of nature or numbers and so on, we're saying there's no such thing in physics. That means that things that we think are constants or numbers can be changed. They're dynamical. You can change them in one region of space to be bigger or smaller. It's not in fixed numbers.
Okay, so constants become fields.
Constants become fields, or more precisely, the expectation value of certain fields.
Right. Okay. Even the speed of light.
Speed of light we view it in a fundamental units as 1, so we don't even talk about it. It's not a speed of light. We view it as 1. It's not changing for any discussion that I'm working. In other words, speed of light is not a. Let me make it more clear. So in your theory, you don't need to have a parameter for speed of light. That just sets the units for us.
So something else will change, but that will change with respect to the speed of light.
Yeah, you could try to do that, but all the parameters in the theory will be somehow related to fields. Now, if you take so now I haven't stated what distance conjecture or duality conjecture is. It tells you that if you take this field and take the value of this field to extreme values, small or large, that means in your physical theory, it might have been a coupling becomes extremely small or extremely large. Something like that. Your theory always breaks down. Always. That's a surprise. That means the extreme limits means something breaks down.
Yes.
Now, what do I mean by breakdown? It means that if you go to far away corners of these extreme parameters, you get a tower of particles which used to be very heavy, becoming lighter, 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 and lighter. And as you go to extreme values, these give you an infinite tower of light particles. Very, very little mass, separated from each other by little masses. And so you have a huge number of particles that you had ignored because back in the middle of the field space, they were very massive. So you could have ignored them. Mm-hmm. But when you go into these extreme parameters, they become so light, you cannot ignore them. And if you try to incorporate them one by one, you cannot succeed because there are infinitely many of them. So therefore, if you go far away to the left or to the right or anywhere, any direction you go, your description breaks down. So what happens? A new description comes over and takes over, incorporating those degrees of freedom, which is not your original description at all. It might mean that some dimensions opened up. It might mean that some extra particles or strings are in the game that you had completely no idea about. This gives us what we call the dual description. So the duality in physics, I just explained to you in a language of this form, is of this form. You start somewhere, you go one limit, you find one description, which is what we call one duality frame. If you go the other direction, you get a completely different perspective, another duality frame. So these physics between them are describing the same physics, but at different extreme regions of parameter space. So this is the duality or distance conjecture, which is also another example. And this does not have to be true without gravity. It's only there if you have gravity. So quantum gravity changes the whole rule. The rules of quantum field theory are not applicable. And that's, I think, the most exciting thing we have learned in string theory. String theory tells you that the paradigm that the particle physicists had been operating for 100 years is badly wrong, because they thought they could ignore the short distance away from large distance. We have learned that you cannot decouple them. The short and large are intricately connected when it comes to gravity. And this is crucial because potentially a lot of the puzzles of particle physics, like hierarchy problem, like all these puzzles that particle physics has difficulty with, that try to use supersymmetry to answer, for example, someone, it didn't work. So many of these puzzles, which doesn't look natural to a particle physicist, is because they had ignored gravity in the discussion. And the reason they ignored gravity was kind of benign. They said, look, gravity is a weak force. It is not strong until you get to Planck energies. And we are not, in our accelerators, we are nowhere near Planck energies. So forget about that. So we're just talking about other particles. Forget about gravity. They thought that not thinking about them is perfectly fine because the energy that we are doing is not related to that. They were not thinking about the connection I told you about black hole. The higher energy and low energy are intricately linked with each other. And that picture is what is, I think, at the root of failure of particle physics to try to explain a lot of these fine-tuning or hierarchies that appear.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, kurtjaimungal.org.